We're going to be expanding our last section that was dealing with proofs with this section 2.6 about basically what do we know that we can prove about angles that are true. So first thing we know that is kind of evident the first time we saw this in terms of the definition for vertical angles is that vertical angles themselves are congruent as a pair. Again, this kind of seems like we know this anyway from looking at a figure, but just by looking at, let's say, like the left and the right hand side of that diagram, angle 1 and angle 3, we know that whatever measure for 1 is, let's say it's like 20 degrees, the measure for 3 would have to match. Those angles would be identical, and that would make them congruent. Same thing is true for the vertical angles at the top and bottom of that intersection as well. If I had, let's say, 160 degrees for angle 2, we know that angle 4 would be identical, so also 160 degrees, which is going to allow us to use that not only in equations, but also some proofs later. So first thing, again, if I'm trying to use this in an equation, I can find the value of x just by applying what we call that vertical angles theorem. Again, that just allows me to say these two measurements are going to be equal to each other. So I know that the expression for the angle on the left is going to be equal to the expression for the angle on the right, again, just by the fact that they're vertical angles. And now that I have this relatively simple algebra equation, I just want to take my steps to solve for x. So if I was to, let's say, subtract 2x from both sides, I get 21 is equal to 2x. This would take one last step to divide both sides by 2, but if I get my answer as 21 over 2, I can also say something like 10.5 for that one as a decimal. That's why I'm going to get my value for x isolated. Again, the only thing we had to start with in that case was just the fact that vertical angles are congruent. That allowed me just to make this equation at the beginning say that left and right hand sides are equal. And we know that it also works for not just left and right, but top and bottom as well. So for the upper and lower angles on this next figure, if I can bring that back over here, 3x is going to be equal to 2x plus 40. Sorry to ruin that for you if you guys already solved that. But yeah, 3x is equal to 2x plus 40. We can make that statement using, again, our vertical angles theorem. Top and bottom are vertical, so they're going to be equal. And then if I subtract 2x from both sides, that's a relatively quick algebra solution, just allowing us to find that x now that's isolated would be a value of 40. So not only can I use this in algebra equations, we can also use these in, remember our two-column proofs from our last section? So this is starting out with a given statement that 1 and 4 are congruent, which notice are not vertical angles, but these would be, for example, like what we call adjacent. And just from starting off with that single statement as a given, we could then show that angle 2 and angle 3, which again have no connection to that first given, just on the face of it, those are going to have to be congruent to each other as well. So don't necessarily have to do this proof yourself. I would just kind of like to cover up my steps as I'm working through this. But let's say if I was to start off with my first statement should be kind of a gimme, because again, we always want to start our proof with what has been given to us as our reasoning. So again, the given statement is exactly what I put in that first blank. That's that angle 1 and angle 4 are congruent. Also helps in some cases to kind of mark your figure as you go. So if I want to mark those with congruency markings, that could be a place that I take that to list that information for the next question. And then for my next statement, again, if we eventually want to show that 2 and 3 are congruent to each other, we want to begin with our thought process, either trying to find a connection between angle 1 and angle 2, which I don't think we can actually say anything about those two just yet. I could try to say something about angle 4 and angle 3. Again, I can't exactly show that those are congruent. We might know that's true, but we have to prove it. So instead, we can try to look for any connection between angle 1 and angle 3 or angle 2 and angle 4. So again, basically we're looking for a way to get from our given information to find a way to prove things about those other two angles. So starting with, like we said, angle 1 and angle 3, you could actually do this in a few different orders. We know that angle 1 and angle 3 are vertical to each other, so that's why I use for my next step in my proof, is that since I know that angle 1 and angle 3 are vertical, that should be enough evidence. Oh, sorry, not angle 1 and angle 3, that comes later, I guess. What I said first in my statement was that 2 and 4, again, for the same reason, are vertical, so that means that I can establish a congruency. And already I know, again, if angle 1 and angle 4 are congruent, I can then just add the same congruency marking for angle 2. So really we know that all of these angles are congruent, but we haven't just used that in the proof yet. Again, you can always use a little bit abbreviations in your proofs as well. So if you want to say like vert instead of vertical, if you want to use like the angle marking, so like angles rather than angles, you can use that to shorten up your work. I just use that congruency symbol for congruent, but again, this is just by using what we call that vertical angle theorem. If they're vertical in our figure, we know they're going to be congruent to each other, so they would have the same measure. So let's say if I wanted to establish, again, another connection. What we can actually use is we can use our first two statements. Again, our eventual goal is to show that 2 and 3 are congruent to each other. But if this is my starting point, that 1 and 4 are congruent, now I can look for connections, like we said, between something like angle 4 and angle 2, which it looks like we have that connection. Angle 4 is congruent to angle 2, again, from the fact that they're vertical. But notice that if both of these angles, 1 and 2, if they're both congruent to angle 4, what we're allowed to say, going back to our last section, is by what we call that, look at our next reasoning, by our transitive property. Again, based on our first two statements, transitive property is that property that allows us to use basically angle 4 as a link between the two. Again, we already know this is congruent based on our figure. We've already marked that 1 and 2 have the same congruency marking. But that transitive property allows us to say that since angle 1 and angle 2 are both congruent to the same angle, transitive property says that they're congruent to each other. So that's yet another congruency I can use to help build my proof. So again, so far we've mentioned angle 2, but again, we want to look for connections with angle 3 as well. So angle 3 we haven't used in any statements yet. So as I look back to the figure, this is actually the rule I was trying to look at first between that connection between 1 and 3. So we know that 1 and 3 are vertical just like 2 and 4 were. So that's what I use for my next statement. Again, with my next step, I want to establish that next connection. So if I know that angle 1 and angle 3 are vertical, again, for the same reason as before, I know they're going to be congruent to each other. So I know that those also vertical angles, we already used that rule again to say 2 and 4 are congruent. We can also use that rule again just to say that 1 and 3 are congruent. And now if I look back at my last two statements, similar to what we've said before, it looks like angle 1 is congruent to the same two angles. So we could use that similar property if we're looking back at what we call that transitive property. We know that angle 2 is going to be congruent to angle 3, which is, again, notice what I'm trying to prove is that those two angles are congruent. And we know that, again, because both of those two angles, 2 and 3, they are congruent to the same angle, angle 1. So transitive property, remember, you want to use that like your linking statement. Again, I said transitive property of congruence, but if you just said transitive, that would be enough on this question. I just need to know that you know what property we're using. And again, transitive is what you think of as that link. We had angle 4 that linked 1 and 2 together. That's why I use that for statement 3, that 1 and 2 are congruent. And then we use that linking statement again, except this time we said that angle 1 was congruent to both angle 2 and angle 3. So that's what we said was congruent on our last step. Again, transitive, you just want to make sure there's a link between the two. In this case, they're both congruent to angle 1. So that means they must also be congruent to each other. Might seem, again, kind of obvious just by looking at the diagram, but notice we've marked the diagram. All of those have the same congruency markings, so we know that those are all going to be congruent. So if I wanted to add in a few more things I can use in a proof, we know we have congruent supplements theorem. So essentially what this proof is telling me, and again, you're just adding in the word there, congruent at the bottom, is that if two angles are supplementary, so 1 and 3 are supplements, I think it's easier to think about this with measures. Let's say if you have like 150 degrees for angle 3 and 30 degrees for angle 1, making them supplementary because they add up to 180. That means that if 2 and 3 are also supplements, that means the missing measure for 2 must have also been a 30. Again, if these two still add up to 180, that's only going to be true if 1 and 2 end up having the same measure. So that we can say is that those supplements, 1 and 2, those are going to be congruent to each other. So essentially this is like saying if I have like that 150 degrees and if I'm missing a certain measure from that to be equal to 180, if I'm missing that same measure from angle 1 and angle 2, those are going to be the same missing measurement. So that would be, for example, like a 30 for each. So 1 and 3 are supplementary. That means if 2 and 3 are also supplementary, that must have been also congruent to each other. Almost how we use transitive property. Again, angle 1 and angle 2 both have that connection to angle 3 because they're both supplementary to angle 3. So we can also do that with complements. Again, difference with complements and supplements is now we just have a different sum. So let's say again that let's say that angle 2 is, let's say it's like 50 degrees. That means if 1 and 2 are complements, then 1 must have been 40 degrees because both of these add up to 90. And if we also know that 3 and 2 are complements, that means that 3 must have been 40 as well. Again, making sure that those add up to 90 again. And just like we saw in our last rule, 1 and 3 are then, by virtue of being complements to the same angle, they're going to be congruent to each other because either way, if we're making 90, we have to add that same measurement every time. So again, if I start with a 50 degrees and I make one pair complementary, it's not going to work unless your other angle is also complementary. It has to have that same measurement. So just knowing that basically the same measure is missing for both. Another rule, kind of like how we use transitive, is just every case that we see right angles, we always know they're congruent to each other, basically because the measure always has to be 90. So if the measures always match, we know they're always going to be congruent. Just another rule that we can add in. And our last rule is saying that if they're congruent and supplementary, so if two angles I see have that same kind of measurement, again, congruent and supplementary, we've marked them congruent. We're also told that they're supplements. The only way we can make that is with two right angles. So again, they're equal to each other. We know they're both 90, and supplementary means they both add up to 180. That is just the one case where I know that both of them are going to be right angles. So we said measure angle 1, measure angle 2, they're the same. They have to be both 90 in that case. So next few examples are really just more practice for what we've already seen. This type of figure is kind of throwing a lot at us, but all we're trying to do is look at the measure of angle 1. And only thing I need for angle 1 is to notice that if it forms this kind of intersection, and if it looks like I have a vertical angle on the other side, only thing I have to do to find angle 1 is to find that vertical angle on the other side of the intersection, and I think that's just going to be that right angle, so it looks like measure of angle 1 would be 90. It's similarly pretty fast to find angle 2 and angle 3. Again, if we're just looking at the vertical pairs there, I think angle 2 is vertical from that 50-degree angle. Again, 2 and 50 just across from each other at that intersection. And same thing if I was looking to answer for angle 3, all I have to do is check what angle is vertical, and it looks like 3 and that angle marked with 40 degrees, those would be vertical to each other. So I already know just based on my very first theorem, that vertical angle theorem, that those vertical angles would have to have the same measure. So next example is also something we talked about from before. Again, just setting them equal because we know that we have vertical angles, so just extra practice. Good to try that one first, but I'll go ahead and reveal the answer. Again, kind of like what we've seen before, we can just use the vertical angle theorem to say that vertical angles should be equal to each other in terms of their measure. And then if I eventually isolate that for x, that's another practice one to get to x is 20. So last problem type, I would say, if I can get that back here, it's probably the one that gives people the most trouble because we do have to be careful about how we use our algebra and set this equation up. So what we're told is just that the measure of angle B is half the measure of its complement, and just by using that as its starting point, we should have enough to find the measure of that angle by itself. So I'm actually going to make two equations here. The first is what we're told, measure of angle B is going to be half the measure of its complement, and I'm just going to call that like measure A for now. So I'm going to say that the measure of B is half the measure of angle A. But then if I'm also told that we have a complement, just that word itself actually implies another equation. The word complement means that the sum of these two angles should be 90 degrees. So what I can also make is an equation. I can add those two together, the measure of both of those two together. Again, unless they're complements, they're not going to add up to 90. So complements implies that that's going to be a second equation I can use. And now that I have two unknowns, we don't know what B or A are, we do at least have two equations, so that should be enough to solve. This is thinking back to Algebra 1. If I wanted to solve, essentially what I'm doing is I can take this equation and I can use my substitution property. I know that B is the same thing as saying half of angle A. So I'm going to go into that first equation and I'm going to start off the same. We're going to say, or sorry, I'm going to go into the second equation rather. I'm going to make this one. So I'm going to set up most of it. We know that measure of A plus another angle is going to make 90. But this time, rather than saying angle B, we're going to make that substitution. We're going to say that B is the same thing as half of the measure of angle A. So now it's an equation I can solve because it's all using that same measurement. If I'm just comparing measure of angle A, I should be able to add these two together as like terms. So a measure plus another half. This would be like saying 3 over 2, or you could also think like 1.5 of that measure of A, whatever it ends up being. That's going to be equal to 90. So if I want to solve this equation, just imagine if this was like a big x there. I have like 3 over 2x that I want to isolate for. So I want to isolate for this measure of the angle expression. I can solve that fast by just multiplying by the reciprocal. That's how I get rid of that fraction coefficient. Again, if this is 3 over 2 times the measure, I can cancel out the 2, cancel out the 3, and then I'm just left with the measure of that angle. And again, this is where I could use my calculator, 90 times 2/3. That I think should give me 60 though. That is the measure of angle A, but I do want to go back and make sure we can find the measure of angle B, the one we're being asked for. Measure of angle B would be using, again, that previous connection we established. B is going to be half of angle A, so it's going to be half of what we already found, which was 60. It looks like B here in this case would be 30 degrees in terms of that measurement. So yeah, a little bit tricky, but just by using that one phrase, there are two equations that we can make. Going back to where we made those equations, again, we're told that the B is half of the complement, so that implies the first equation. B is half of whatever the other angle is. And then just the fact that they're complements tells me that they should both add up to 90 for their measures. So that allows me to make two equations. Again, what we did was we used that replacement. If I know that B is worth half of A, I can go back and substitute that into that second equation. Then it becomes solvable. Just to reveal that second answer, again, not really much changing besides the connection between the two. Now I know it's 3 times rather than half as large as the second angle. We also know we're dealing with supplements now rather than complements. So if I was to put that information together, again, essentially the setup is similar. We know that whatever angle A is, it's going to be 3 times the measure of your second angle. And if I know I add them both together, now that they're supplements, that's going to make 180. So I use substitution. I substituted in that expression, 3 times that measure of angle B. I solved that for the first angle, went back and I substituted back into that expression. So I know it's 3 times that other angle. And that's what finally told me that value, that angle A is 135.